This video covers sections 22.6 to 22.9. We start out with the preparation of amines via reductive amination. And the way this works is that we start with a carbonyl compound, we treat it with ammonia in acidic conditions, and that forms the imine, which we can reduce to the amine using hydrogen and palladium or sodium sodium cyanide borohydride. And why do we use this reagent? This is a milder reducing agent than sodium borohydride, and it's commonly employed in reduction of imides. Now I want you to practice the product of the following reaction sequence. Pause your video and see if you can come up with the answer. This is the product. Let's see how we got there. Our first step is to form the imine. Then we do our reduction. And finally, this is followed by an alkylation. Here we're using 1 equivalent of methyl iodide. With 22.7, we're going to skip this section in the video, but you should read it and do the practice problems. This section is on synthetic strategies. Next, we're going to discuss the acylation of amines and how it's useful in multi-step reactions. If we take an amine and an acid chloride and combine them, then we get an amide product. This is useful if we want to tone down the reactivity of an aniline compound with in an electrophilic aromatic substitution reaction. For example, when we treat aniline with bromine and FeBr3, then we see that there are multiple brominations in this system. What if we want monobromination? Then we need to acylate the compound. So first we're treating the amine with acid chloride to form the amide. We then do a bromination, which now that the reactivity is toned down, only gives the para-substituted product. And then finally we use protonated water or acidic water or sodium hydroxide to remove that amide group through hydrolysis to get to aminobromobenzene. It's also useful in Friedel-Crafts alkylations or acylations. If you treat aniline with an alkylating agent and aluminum chloride, then what you get is the formation of this complex where the nitrogen has reacted with aluminum chloride. And that's no good because it turns it not only consumes the aluminum chloride, but it turns this compound into a deactivating group. The solution to this problem is to acylate the aniline, forming our amide. Then we do the Friedel-Crafts alkylation in this case. And finally, we do a hydrolysis with acidic water or sodium hydroxide to get our aminomethylbenzene. Here's a practice problem. When aniline is treated with nitric acid and sulfuric acid, the product that forms is not the para-substituted nitro or aminonitrobenzene, but rather the meta-substituted version forms. Why is this the case? Propose a route to synthesize para-aminonitrobenzene. So when the nitrobenzene is treated with sulfuric and nitric acid, what we get is the protonation of the amine, and now we have a quaternary ion, and this is meta-directing. So it gives us the meta-substituted product. Instead of this, we can treat the compound with an acid chloride. Then we do our treatment with nitric acid and sulfuric acid. Then we can treat with acidic water or sodium hydroxide to undergo a hydrolysis reaction, and then we recover our amino group. So here we've successfully made para-aminonitrobenzene. The next reaction and last reaction we're going to cover is Hofmann elimination. Amines can serve as a starting material for alkenes just as alcohols can. How? We're going to alkylate our starting amine to give a quaternary salt. Then we're going to use silver oxide with water and heat to form our alkene. Why does this work? It's because NH3 or the trimethyl ammonium group is a great leaving group because it produces neutral trimethylamine. Hofmann eliminations yield the less substituted alkene or least substituted alkene if there are three choices. So, for example, we have the conversion of this nitro or this amino pentane, 2-aminopentane, and instead of forming the more substituted product, we form the least substituted product. Why is this? It's because the energy, the activation energy to form the less substituted compound is lower. So here we're following this energy diagram, and we see that we have an activation energy that is taller than the activation energy to form the less substituted alkene. To get an idea of why the activation energy is lower for the less substituted alkene, we need to look at Newman projections. To get to the more substituted product, you need to have the compound positioned where the leaving group is antiparaplanar to a hydrogen atom. So that puts the butyl group closer to the amine. And so whether you use this hydrogen or this hydrogen, you're going to have a gauche interaction. However, if you look at the less substituted product, then we draw our Newman projection like this, and we don't have any gauche interactions. Why is this not the case for alkyl halides? It's because their leaving groups are smaller, so the gauche interactions don't matter as much as they do with the ammonium compound. Okay, our last slide is a practice. Consider the halide salts and ammonium salts, which would accomplish the following transformation. Or I should say, that would make the following alkene. So in each case you have two choices, but not all of them will work. Let's start with our alkyl halides. And we'll put a bromine atom on either side of that alkene. Both of these reactions work. You just need a strong base, and you'll form the more substituted alkene. You want to make sure in this case that your base is not bulky, because if it were bulky, then you'd put the alkene here. Let's look at putting the trimethylammonium group on both sides of where the alkene forms. The first example is going to work, but the second one will not. What product do we form instead? Well, we know we want to form the less substituted alkene, and in this case we didn't have a choice because we would either form an alkene here or here. So we have the same result. But in this case we have to consider whether the alkene is going to form here or here, and we want to get to the most substituted product, or sorry, the least substituted product. So this compound does not work because it gives us the wrong alkene. That's all for this video. Have a great day.